normal strain along 2, one will be straight away because of sigma 2 by E2, and there will be nu 1 to sigma 1 by E1. Please go back and check the lecture 1 of module 3. Okay. Because how do we define Poisson's ratio? Nu 1 2 is equal to minus epsilon 2 by epsilon 1 when only sigma 1 is acting. Therefore, epsilon 2 is equal to minus nu 1 to epsilon 1. What is epsilon 1? Nu 1 to sigma 1 by E1. Therefore, we have written this is the strain along 2 because of sigma 1. Similarly, by the definition of Poisson's ratio, nu 2 1 is equal to minus epsilon 1 by epsilon 2 when only sigma 2 is acting. All other states are 0, which means epsilon 1 is equal to minus nu 2 1 into epsilon 2 is equal to minus nu 2 1. Epsilon 2 means sigma 2 by E2. So this is what we have written here. Okay, and then in an orthotropic lamina, there is no extension shear coupling. So shear strain gamma 1 2 is equal to tau 1 2 by G 1 2. Okay, so if you combine this gives us epsilon 1, epsilon 2, gamma 1 2 is equal to 1 by E1 minus nu 2 1 by E2 0 minus nu 1 2 by E1 1 by E2 0 0 0 1 by G1 2. So from this you can actually make out what are the elements of the S matrix in terms of 4 engineering constants. So given this, we can now write what is S1? This is S1, S11. What is S22? This is S22. What is S12? This is S12. Therefore, S11 is equal to 1 by E1. S12. Of course, S12 is equal to S21. Nu 12 by E1 or nu 21 by E2, same thing. S22 is equal to 1 by, sorry, S66. S22 is equal to S22 is equal to 1 by E2, 1 by E2, and S66 is equal to 1 by G12. All others are 0. S16. So that is what is. If you know E1, E2, G12, nu12, you can immediately find out what is S11, what is S12, what is S22, S66. And then you have the transformation formula. Again, I am reiterating, you don't have to remember those transformation formula. This will be given. But if we know in the material axis, we can find out in the global axis by using this transformation formula, which is given in the lecture. You can see that formula, okay? S11 bar is equal to S11 cos to the power 4 theta, like that, okay? So in terms of sin theta and cos theta, those transformations are there. So this is how we actually calculate the S bar matrix given the 4 independent engineering elastic constants for a lamina. I hope that is clear. Is that clear? Let me see. First lecture 11th week, the free stresses for minus between since epsilon not y non-zero. Could you please elaborate how sigma y becomes 0? Oh. Before that, is that clear what I have explained? Who has asked that question? Some Bharati or okay. What is that question? Plus minus theta symmetric laminate. Could you please elaborate on how sigma y becomes 0? What sigma y becomes 0? Oh, okay, okay. Okay. Tau xy sigma y. Hello. 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 Somebody has asked about that free edge stresses. Yeah. So just who was that?
Yes.
Yeah, Nathan, right?
Yes.
So if you apply a, load along x-axis, there will be strain along y-axis because of the Poisson's effect. Okay. Now, in case of plus minus theta, there is no mismatch in Poisson's ratio mu xy. If there is no mismatch in the Poisson's ratio, then there will not be any stress. There will be strain, but there will not be any stress. Is that clear? Suppose if you just take a simple isotropic material, suppose if you stress it along x direction, so there will be sigma x, but in the y direction there will be strain. But if you do not restrain it, there will be no stress. Same is the case here. So here, because it is plus minus theta, there is no mismatch in Poisson's ratio. Therefore, there will not be any stress in the y direction, even though there is strain. Strain will be there because of the Poisson's effect, but there will not be any stress. Stress would have been there had the Poisson's ratio been different. That means we are restraining it. Suppose the Poisson's ratio of between the two layers are actually different, then there would have been stress in both the layers. Even though the net force would have been 0, but the stress would have been there in both the layers. Is that clear?
Yes, sir.
Yeah, please try to do that, and you'll get convinced. Why stresses actually come? Stress will come only when you restrain it. Why from the restraint comes? If the two layers are not allowed to expand or contract freely. Now, because of Poisson's ratio, because the Poisson's ratio is same for both the layers, therefore they are free. I mean, they are not restrained. Therefore, there will not be any stress. Okay. Any other question?
And yeah. Sir, also, do we need to remember the formulas for the vibration or the Q-bar matrix or DX?
I'm not getting your. Could you be a little louder?
So, do we need to remember the formulas for the Q-bar or the S matrices or the vibration formulas in the exam, or will they be given to us?
No. I told number of times, even in the last few meetings, that you don't have to remember any of these formulae, excepting very few. The basic relations like sigma is equal to E into epsilon, or epsilon is equal to sigma by E. Other than that, you don't have to, remember any formula. If any formula is required, that will be given.
Okay. Yes. Thank you.
Okay. Please explain how to calculate matrix. Yes. There is a question from Nalini. Please explain how to calculate metal stresses in question number 4 of assignment number 10. I'll have to again go back and see the assignment number 10. Just a minute. Could you see? Just 1 minute. I'll first check that anyway, and then let me see other questions in the meantime. Okay. Any other question? Yeah. During the exam, will some of the formula I told you already. This test is not to test your recall capacity, your capability to memorize the, no, it is basically conceptual. That's what. If any formula is required, that will be given. Of course, some basic formulas. Again, I'm telling that suppose that alpha into delta T is the thermal state. That you need to know. Other than that, this transformation and all, no, you don't have to remember anything. Such big formula. Just a minute, I'm just seeing that. But just which one? How to calculate metal axis stress in question number 4, assignment number 10. Let me see. Assignment number 10, question number 4. When a pressure vessel is made from this carbon epoxy is subjected to internal pressure of this, the metal axis stresses induced in the 90-degree plies are. So what is I think in the macromechanics we have done it number of times, right? We have done it number of times, the metal axis stress. I think this one. See, if you know the metal axis stress in question number 4, metal axis stress means what? If you know the global stresses, you can always use the stress transformation, isn't it? Sigma 1, sigma 2, tau 1, 2 is equal to T. T is a function of theta. You don't have to again remember those transformation matrix that will be given if required. Okay, so those will be given if it is required. But metal axis stress means you find out the stress with respect to 1, 2. Given the stress in XY, so you just multiply the transformation matrix. That's all.
Like if you know the metal axis strain directly by the Q matrix.
No, but she has asked that explain how to calculate metal axis stresses in question number 4 of assignment number 10. Okay, because if you know the metal axis strain, you just multiply it by the Q matrix. Q, not Q bar. Given epsilon 1, epsilon 2, gamma 1, 2, then sigma 1, sigma 2. Just 1 minute. If you have the metal axis strains, metal axis strains epsilon 1, epsilon 2, gamma 1, 2, then the metal axis stress sigma 1, sigma 2, tau 1, 2 is nothing but multiplied by Q matrix, Q11, Q12, 0, Q22, 0, Q66, epsilon 1, epsilon 2, gamma 1, 2. That's all. And if you know now what is metal axis and what is global axis, that I think I'm again reiterating. I'm sure all of you know by this time. This is the global axis or analysis axis, and this is metal axis. So what we know is this theta. Okay. Now, if we know the metal axis strain, straight away multiplied by the Q matrix, reduced stiffness matrix. Okay. If you know the global axis stresses, then just simply use the transformation matrix to find out the metal axis stresses. Multiplied by T matrix. That T is the stress transformation matrix, which is nothing but function of sine theta, cos theta. Okay. So this is a function of theta, sine theta, cos theta. I think anyway, you don't have to remember this matrix, but knowing this theta, if I know the stresses with respect to xy, sigma x, sigma y, tau xy, I can find out what is sigma 1, sigma 2, tau 1, 2. How? Just multiply it by the transformation matrix. For that, I must know what is T. T is a function of theta. Sine square theta, cos square theta, twice sine theta, cos theta, like that matrix. But you don't have to remember that. This will be given if required. I suppose I could answer your question. Any other question?
Sir,
Yes, Shiva, please.
sir, can you just give us a small description about classical lamination theory, like the elements?
Pardon? Come again, please.
Classical lamination theory. Can you just give what's like the elements in it? Just a small gist of
What element?
like what's in it. Like, can you describe classical lamination theory, sir?
You want me to? I cannot derive classical lamination theory in 5 minutes. But anyway, I'll tell you what exactly it is, because it itself takes one class. I think more than one classes. So, what exactly your question is? Maybe I'll try to tell you in brief what is classical lamination theory. Let me see if I could do something in 10 minutes. So, in classical lamination theory, basically we make certain assumptions, simplified assumptions, that mainly that laminate is thin, okay, it's perfectly bonded, okay, and we neglect the transverse shear, okay, and with those assumptions, basically we actually, assume a displacement field. What is that assumption? If you remember, I can do it quickly. Suppose this is a laminate, okay, we always put our coordinate axis at the mid surface of the laminate, x, y, and z. Okay, this is the thickness of the laminate. Okay, so with all those assumptions, what we assume is U0 is the mid surface x component of the displacement, V0 is the displacement of the mid surface in the y direction, and W is the displacement in the z direction, and we assume that U0, V0 are actually functions of x and y, okay, and W is equal to dot. That means the z direction displacements of the mid surface and the z direction displacements of any other point, that means the top and bottom surface, is same. This is true because the laminate is thin, and with that assumptions, what we get is actually we get that epsilon, that means the strain at any z is actually a function of epsilon naught, that means mid surface strain, plus z k. Now this is actually all the three components of strains, say epsilon x, epsilon y, gamma xy. This is strains, and this is curvature. So what we get is that the strains actually vary linearly with z, okay, and this is a straight away an outcome of our displacement field assumptions. Then what we do is we try to find out the stress, but then you'll appreciate that in a layered laminate we have n number of layers. Even though the strain distribution is linear, that means it's a linear function of z, this is a strain, but the stresses are different in different layers. Why? Because how do we get stress? Stress is nothing but, suppose for kth layer, say this is kth layer, okay, where k going from 1 to n number of layers. Therefore, stress in the kth layer is nothing but Q bar, that is the reduced transform stiffness matrix of the kth layer, and the strain in the kth layer. Now, this is different in each of these layers, okay? Therefore, the stresses will not be continuous. So, stress variation may be like this, depending upon the values of. Therefore, it is not that easy to have a straight away the stress and strain representation. So, what we do is you just go through the lecture. I think it is nicely explained. So, what we do is we take an equivalent system, because we cannot relate the stress and strain like this, because stress is not continuous across the layers. So, what we do is we represent all these stresses as stress resultant. That means which is the sum of all the stresses across the thickness. Okay, we sum all the stresses across the thickness and we say this is the force resultant. Okay, this is equivalent system. That means suppose you have 3 layers. Suppose each layer is having defined stresses. We add them all and we say that in this 3 layer, okay, there is a single force which is equivalent to this. That is what is, statically equivalent system. Similarly, we also write a moment of, because there are different stresses in different layers, so there will be a net moment, and this is again Z dz. Please note that these are the 3 stresses: sigma x, sigma y, tau xy. Similarly, here also there are 3 stresses. Similarly, this is 3 forces. Okay, so these are statically equivalent system. That means the stresses in different layers are actually represented by a single force which actually acts at the mid surface, and by a single moment. Single moment means there will be actually 3 moments because of 3 stresses. Corresponding to each stress, there will be 1 moment. This force and moment actually acts at the mid surface. So finally, this laminate analysis boils down to, if I just draw the mid surface, this is the mid surface of the laminate. So there are, it is subjected to Nx, it is subjected to Ny, it is subjected to Nxy. Also, it is subjected to, for clumsiness, I'm showing in a different, it is subjected to Mx, it is subjected to My, it is also subjected to twisting moment Mxy. And then we could correlate this force and moment to the mid-surface strains and curvatures. This is what is the basis of classical lamination theory. And finally, what we get is N, of course, N is a 3x1 vector. And M is also a 3x1 vector, is related to AB, related to the mid-surface strains and curvatures by the so-called ABBD matrix. That this is the characteristics matrix of the laminate. Why? Given the force and moment, we can immediately find out what is the mid-surface strains and curvature. Suppose you take a laminate which is subjected to, say, only one force, say Nx, say 100 kilonewton. So if the force is 100 kilonewton, we can find out what exactly is Nx. What will be Nx? Tell me. Nx is actually force per unit length. Suppose this is, say, B, the width of the laminate, then Nx will be 100 kilonewton by, say, the B is equal to say 50 mm. So say 0.0, say the width is say 0.5 meters. Say, therefore, this is the Nx. Okay, 100 kilonewton by 0.5. Okay, kilonewton per meter. Okay, so we know what is Nx. Now we would like to know what is the response of this laminate. Now in this ABBD matrix is already known. How we know ABBD matrix? Because all these are actually functions of Q bar, then Z Q bar K for each layer, distance of each layer ZK and ZK minus 1, that is the distance of the top surface and bottom surface. Okay, and then we can find out each element of this ABBD matrix. Okay, we know the expressions for ABBD, A, B, and D matrix. So knowing this, suppose this is the laminate which is subject to only Nx, then what is the force vector? All others are set 0. Say 100 kilonewton per meter, Ny is 0, Nxy is 0, Mx is 0, My is 0, Mxy is 0, is equal to, we can write all the elements of the ABBD matrix into epsilon x naught, epsilon y naught, gamma x y naught, okay, kx curvature, ky curvature, kxy. We take this inverse, we can find out all these epsilon x naught, epsilon y naught, all these strains and curvatures. These are mid-surface strains and curvatures. Knowing these mid-surface strains and curvatures, we can find out the strains in any other layer by this. If I know these mid-surface strains and curvatures from this equation, we can find out the strain in any other layer provided we know the distance of this layer Zk from the mid-surface. So what do we do with that? Knowing the strain, we can find out the stress in that layer. What do we do with the stress? If we know the stress in each layer, we can apply the failure theories to assess whether that particular lamina is safe or not. You have studied in macromechanics of lamina. That is in brief the use of classical lamination theory. Again, this is based on certain assumptions, but it actually gives an ABBD matrix. And looking at the ABBD matrix, we have discussed in details, we can characterize the matrix. making some of the elements 0, we can actually obtain the desired behavior of a laminate. Suppose we don't want the bending extension coupling, we can make B to be 0, and that laminate is called symmetric laminate. Please go through the lecture again, and I'm sure it will be clear.
Yes, sir.
Some idea about that?
Yes, sir. Fine, sir. Fine.
Please go through that. Go through that, and if required, you can go through book also. Okay. So I think I'll stop today here because it's 3:45. I'm supposed to take up to 3:45. Okay.
Sir, one last.
Yeah.
Like, can you share any previous year question papers, sir?
No. This is the first time I'm offering this course. No previous year question paper. Only thing is that this will be. See, again, I'm telling you, go through the lectures. All these are conceptual questions. It is you don't have to remember any formula. Therefore, I'm sure if you have followed the lectures, you'll be doing well. There is no issue in that.
Okay, sir. Thank you, sir.
Okay. All the best to all of you for the exam. Thank you.